everyone, good day. I am Chinchin A. Tuting, a BS Mathematics student, first year at Negros Oriental State University. In this video, I will discuss the four basic methods of proof, which are direct proof, proof by contradiction, proof by contrapositive, and principle by mathematical induction or PMI, by providing examples of each methods of proof.
Alright, so I will begin in direct proof. So here, we will assume that P is true. So then we'll build an argument using a chain of implications leading directly to the conclusion that Q is a true statement. So by following the outline for direct proof, my chosen problem is if L and M are odd integers, then Lm is an odd integers. So to directly prove it, we'll assume that L and M are odd integers. Then by definition, M is equal to 2a plus 1 for some integer a, and L is equal to 2b plus 1 for some integer b. So remember that we need to use different integers a and b in the definitions of L and M. So we will now use this to show that Lm is also an odd integers. So we have our definitions of Lm. So Lm is equal to 2a plus 1 times the quantity 2b plus 1. So we will expand the brackets. So we have now 4ab plus 2a plus 2b plus 1. So since 2 is the common factor, we can rewrite this as 2 times quantity 2ab plus a plus b plus 1. So therefore, Lm has the form of an odd integer since 2ab plus a plus b is an integer. Okay, so moving on to the next example, which is indirect proof using proof by contradiction. Okay, so here it is based on the fact that a statement is either true or false. By definition, this means that P is true and Q is false. Then we build an argument that leads to a contradiction. Alright, so here is an example. If a squared is even, then a is even. So proof by contradiction, assume a squared is even but a is odd. Okay, so since a is odd, a is equal to 2b plus 1 for some integer b. Then a squared is equal to 2b plus 1 raised to 2. Then we will expand this. So we have 4b squared plus 4b plus 1. Then we can rewrite this as 2 times quantity 2b squared plus 2b plus 1. Now we let c is equal to 2b squared plus 2b. Then a squared is equal to 2n plus 1. So by definition, a squared is odd. But this is clearly impossible since a squared is even. So we have reached a contradiction. So our assumption was false. Thus, if a squared is even, a is even as well. Alright, so next example is an example of proof by contrapositive. So this uses the fact that an implication and its contrapositive are equivalent. So example, if a squared is even, then a is even. So proof by contrapositive, we prove that if a is odd, then a squared is odd. Okay, so since a is odd, we have a is equal to 2n plus 1 for some integer n. Then our definition of a squared is equal to 2n plus 1 raised to 2. Then we can expand this as 4n squared plus 4n plus 1. Then we can rewrite this as 2 times quantity 2n squared plus 2n plus 1. Okay, so since 2n squared plus 2n is an integer, therefore a squared is odd. Alright, so lastly, is an example of principle by mathematical induction. Okay, so we have the distributive law from algebra says that for all real numbers b y sub 1 and y sub 2, we have b times quantity y sub 1 plus y sub 2 is equal to by sub 1 plus by sub 2. Okay, so use this law and mathematical induction to prove that for all natural numbers n is greater than or equal to 2 if b, y sub 1, y sub 2, y sub n are any real numbers, then b times quantity y sub 1 plus y sub 2 plus plus y sub n is equal to by sub 1 plus by sub 2 plus plus by sub n. Okay, so the solution goes like this. So first, we'll let p of n be the given statement like p of n such that b times quantity y sub 1 plus y sub 2 plus plus y sub n is equal to by sub 1 plus by sub 2 plus plus by sub n. For all natural numbers, n is greater or equal to 2. For b, y sub 1, y sub 2 y sub n for some real numbers. Okay, so we observe that p of 2 is true since b times quantity y sub 1 plus y sub 2 is equal to by sub 1 plus by sub 2. Okay, so next, we will assume that p of n is true for some natural number k where k is greater to 2. Like p of k such that b times quantity y sub 1 plus y sub 2 plus y plus y sub k. So equals by sub 1 plus by sub 2 plus plus by sub k. Okay, so then now to prove p of k plus 1 is true, we have p of k plus 1 such that b times quantity y sub 1 plus y sub 2 plus plus y sub k plus y sub k plus 1 is equal to b times quantity y sub 1 plus y sub 2 plus plus y sub k close parenthesis plus y sub k plus 1. Then multiply b times quantity y sub 1 plus y sub 2 plus plus y sub k plus by sub k plus 1. Okay, alright, so now we will simplify this. We have b times y sub 1, we have by sub 1, then by sub 2, b times y sub 2 is equal to by sub 2. So that's why we have by sub 1 plus by sub 2 plus plus by sub k, then copy by sub k plus 1. So thus p of k plus 1 is true whenever p of k is true. Hence, by principle of mathematical induction, p of n is true for all natural numbers n is greater or equal to 2.
Thank you for watching and have a great day, everyone.